If you enjoy Astronomy FM radio, please let us know with a small donation. We do rely on your support, and it's true. Every little bit counts.
AFM. You're listening to AFM radio on Astronomy.FM. Around the world and beyond.
Coming up next, it's time for an AFM radio original program, Space Pirate Radio, brought to you by the voice of astronomy, matey. This is Astronomy.FM.
The pirates are coming. The pirates are coming. The pirates are coming.
Arr!
Arr!
Arr! All right, it's Space Pirate Radio time. Buckos here on Astronomy.FM radio. That means it is another Wednesday evening, and this one is January the 24th, 2018, 9 o'clock in the evening for those of us here in the eastern portion of North America. Also known, universally speaking, it is January the 25th, 2018, 2 o'clock in the morning, universal time. So if that's your time right now, that means you're listening to us live. And, of course, that means we have our Astronomy.FM radio chat room open right now. So come on over and join us. You can go to the homepage. Look where it says radio chat. Click on that. Type in a name, hit login, and you'll be here in our chat room. If you want to communicate with us.
Tonight.
It is a whole crew tonight, yes. So if you want to communicate with us, you can type something in there, and we'll be able to read it. And if you have questions for us, feel free to ask us questions as we go along. So far, we've got you and me and 332603. See, you can do it anonymously, too. Black Projects. You got Jerry Hubble, which is our guest tonight. We'll get into that real soon. Twist Edge Glenn, 712564, another anonymous person. Doug from Northern Cross Observatory. And Plaid Mac. You're all considered part of our crew when you join us in the chat room during the live portion of the show. And, of course, don't forget, we'll repeat this program every 4 hours for the next 24 hours with some more programming. We'll get into that. I got to mention an anniversary tonight. The anniversary of Opportunity. 13th anniversary of landing on Mars.
Pretty darn good for a 90-day mission.
Not so bad at all. Yes. Mm-hmm. Oh, well, should officially announce our guest. We have Jerry Hubble. He's from Explore Scientific. The Rock, what's the astronomy club?
Rappahannock
Astronomy Club, and the Mark Slade Remote Observatory. Mm-hmm.
And if you want to check out the Rappahannock Astronomy Club, it is raclub.org.
There you go.
We'll be sharing that with y'all.
Yes, indeed. All right, awesome. Jerry. You've got some new projects we'll start out with the observatory, what you've been doing there. You got some new equipment, new projects going on. Then we'll talk maybe a little bit about where you work and stuff like that. So let's jump right into the observatory.
Yeah, I want to thank you, Marty, and Dianne for inviting me back on. I appreciate the opportunity to talk to everybody about what we do at Explore Scientific and also to talk about the Mark Slade Remote Observatory. We have been doing some upgrades recently. The observatory is designed as a learning system to teach people how to more hands-on observing and astrophotography, and also to do science. And so, in that regard, we're able to remotely connect to it with multiple people and teach people real time, basically how to manipulate all the controls on the system. And so it's really a cool system like that. And one of the things we've gone through a few instruments in the last 2 years. We put it online about almost 2 years ago, and we started out with a 12-inch Meade Schmidt Cassegrain LX200 on a fork mount, and then we moved last year, about a year ago, to a Losmandy G11 mount with a new control system that I designed and built for Explore Scientific called the PMC-8, and we put our 6-inch 152 Apo refractor on it. And then just recently we updated that telescope to our new 165 millimeter 6.5-inch Apo refractor that has a high-end FPL 53 glass in it, which is a very, very nice system. So that's our major instrument upgrade this year that we've done. We do have also on top, we mounted our FCD 100 version of our 102 millimeter apo-refractor carbon fiber. Both these scopes are carbon fiber. So those are the two main changes we've made in the last few months.
So that's extra 4-inch you've mounted on top of it.
That's right. So we've got a 4-inch scope. That's a wide field astrophotography with a color, one-shot color camera on it. It's got a 16 megapixel color chip on it, and then we've got our venerable big ST2000 camera, ST2000 XM camera, which is about 12 years old, and it still does great work on our main instrument.
So the improvement is for more resolution, a little bit more light gathering. What was the main reasons?
Well, we wanted to be able to demonstrate our latest instrument on the observatory and show people what it's capable of. And like you said, it's got a little bit more light gathering. It amounts to about 17% more light from a 6 to a 6.5 inch upgrade. And then the optics are very sharp, very crisp, and it's very noticeable on the imaging because we can actually get, when the seeing is good, you can actually focus tighter stars on it. And we've coupled that with our 0.7 times focal reducer field flattener. So the effective focal ratio on this system is f4.9, which is pretty fast. So it's 6.5 inch f4.9, and that's an equivalent focal length of about 809 millimeters.
So tying into that, Jerry, we do have a question already in the chat room from Glenn, one of our supporters and donors, and he wants to know what the greatest magnification of the main telescope is.
That's an interesting question, and it's really, magnification really involves visual observing, not really so much astrophotography. I would say if you were to use an eyepiece on it, since this has got very high-end glass and it's a very crisp image, you can, if you've got a bright enough object like the moon, let's say, or a planet, you can really push the magnification up very high. I think the typical rule of thumb for a standard telescope is like 50 power per inch. I think you could probably push this up over 100 times per inch. Nice. Right. So that would be up to around 600 power. Now, of course, that you're seeing really is a limit there. But for visual use, I imagine on the moon or a planet, you could push it up to close to 600 power pretty easily.
One test I do on the moon once in a while is I try to see the smallest possible crater with my telescope. So crank the scope, how well the scope's working, cranking up the power with the air condition, condition to the sky and stuff like that. All has to be in a good combination to give you the best little dot of a crater. Interesting challenge.
Oh yeah.
So that scope would be good for double star work too, wouldn't it?
Oh, absolutely. Yeah, and that would be really nice for that, for sure.
As Doug's just saying in our chat room, splitting doubles are a good measure of seeing also. Yeah. So how long have you had it hooked? This new scope was only been up for a couple weeks, right?
Yeah, we actually installed it on New Year's Eve this year. So, and a whole group, there's 4 of us that got together at the observatory to take the old scope down, the old instrument down, and pull the cameras off and everything. And then we had to move we've got a precision focuser system from Moonlight on it. So we had to pull that focuser off and with the flange and put that flange on the new scope, on the carbon fiber scope, and then mount the focuser and get all the instruments back mounted on and put it installed into the observatory. It took about 2 to 3 hours, I think.
Must obviously be a motorized focuser. Yeah.
It's a Moonlight precision motorized stepper motor focuser. It's very precise. It's a 4 micron per step motion. So it's very tiny movements. And typically we can see a difference like we were talking before the show, Marty, I was telling you how crisp the focus is. When you move it, you'll know it's right on focus.
Uh-huh.
And with the focal ratio of f4.9, it's very narrow focus range. So you basically, we probably got like a 10 or 20 step range where it's noticeably out of focus if you don't get it within that margin. So that's like, 50 microns maybe.
Mm-hmm.
That's how tight the focus position is. Got to be within 25, 50 microns maybe.
So if you're looking through visually, you would know that you're either focused or not focused.
Right.
At one click of your little focus or not.
Right. So.
But you're hooked up to camera, so you're doing all your focusing through the camera, though.
Right, exactly. And we do that by just measuring the size of the blob, basically, on the star when it creates an image on the CCD. When you go in and out of focus, the star image gets bigger and smaller, and then you try to minimize the size, basically. And that's called the full width at half maximum, is how we measure that.
Mm-hmm. When all the light is concentrated the most.
Right. Mm-hmm. Exactly.
And I see you had
the astrophotographers are out there. That's the interesting thing is you got tons of observers, but probably 5% are astrophotographers. Most people are visual, as far as that's basically the impression I get talking to people.
Yeah, generally in a club, yeah. Our astronomy club has quite a few astrophotographers, like Doug, that's in our chat room right now.
Mm-hmm.
But me, yeah, not so much. I don't have the equipment for it anymore, too. So, yeah, you sent me a picture, I think, just recently of the Orion Nebula, wasn't it?
Oh yeah. That's one I took the other day on the 20th.
It's on the Facebook page, right? Gary?
Yeah, exactly.
Yeah, you've got some beautiful stuff there on the Facebook page.
Yeah, I was just doing some testing. Now, what happened on Friday night? Bart Ballard and I were doing some work on an exoplanet, and our shutter failed on us on the dome. So Saturday we had to fix it. The cable came loose on the attachment point on the dome. It failed, and Saturday Myron and I had to work on it for about 2 or 3 hours to get it fixed. And then that night, Saturday night, I was just making sure everything was correct and back working. And I just screwed over to the Orion Nebula and decided just to do 30 minutes on it. And the seeing wasn't the greatest. And I just decided to snap some frames and then compile them. And that's what came out. And it turned out really nice.
It did. That was the S-Big camera, right?
Yes, that's right.
And
that's no, that's a luminance filter, but basically no filter.
No filter, yep. Who said duct tape?
But that camera still performs.
Mm-hmm. Nice. Do you have a filter wheel for it? Do you do some color work with it?
I do V-band photometry with it. Okay. We do have a red and a green filter, and we just recently, that's one of the other upgrades we did. We had a standard green filter on it. We just switched out for a V-band photometric filter that one of our observers, the MSRO, he purchased for us and donated the use of that for the observatory. So we installed that in place of the green filter. So we have that available.
Want to explain them in a little bit more detail, the difference between the two filters?
Yeah, a green filter is like a standard color filter that like in a one-shot color camera, you got RGB Bayer matrix overlay. So the RGB filters you get for filter wheels is the same kind of filter. It's a standard green filter. I'm not sure what the bandpass is, but a V-band photometric filter is a calibrated filter, so to speak. It meets a higher standard for bandpass and wavelength and center wavelength, and basically what that filter is designed to do is to be able to take measurements with it or observations with that filter, and then compare them with other people's data that they've taken with the same type of filter. So it's really used in science imaging more than just pretty picture imaging, although you can use it in pretty picture imaging as a green filter. And what it was designed to be was a close match to what your visual what your eye actually sees when you're looking at if you're doing a variable star measurement with your naked eye.
Ah.
It was meant to be able to cross over that measurement and to a CCD image, or even a photoelectric photometer measurement. So it was supposed to be similar in bandpass to what your eye is sensitive to in the green.
But it's a much tighter filter.
Yeah, I imagine it's probably got a narrower bandpass. Is that what you mean?
Yeah. Yep. So
yeah.
So basically, it lets a lot of the stray colors in.
Well, it would block everything else except for that green. Is it?
Yep.
Yep.
The standard filter, Glenn was asking, would be like a moon filter. Yes, Glenn, like a moon filter would be the standard green.
Oh, I see. The moon. Yeah, I remember those filters.
As opposed to one of the green gel filters.
Right.
That you might use to look at Mars.
Mm-hmm.
Right. Mm-hmm.
And then it's just for the photometry, it's just a much better quality of.
Yeah, it just lets you be able to tie your measurements into a standard system, basically a standard measurement system. It's like a calibrated filter, basically, is what it comes down to, although there's some adjustments. But overall, it's like having a calibration standard for color.
So that you said you do photometry work with this filter?
Right. Yep.
So basically, you just use that one filter, no matter what the star is more sensitive in. But it's an easy way of calibrating your observations with everybody else is using the same filter, right?
Right. Exactly. So when we measure, there's other instrument errors, but overall, if you were to measure a star, no matter what the type is,
mm-hmm.
what the color is, in the visual band, you should be able to match that magnitude value to the reference magnitude and say, okay, I know what my measured value is, and this is what the reference value is for that measurement. You can tie those two numbers together, or basically normalize it to that one reference, and then you can go measure other objects in the frame and say, oh, okay, this is what the magnitude of this object is now, like an asteroid.
Mm-hmm.
So now you basically calibrated your frame to that reference standard, and now you can go over to an asteroid and say, okay, I measured this asteroid at this position, and I measured this magnitude for that asteroid to within probably well below probably 0.05 magnitude or better, maybe,
mm-hmm.
As an absolute value. Differential measurements are always more precise, but for an absolute value, you can get a asteroid value pretty close. I mean, 0.05 magnitude.
And you're doing this with your CCD camera.
Right. Mm-hmm.
Glenn's asking, does distance matter? Distance to the object? No, as Jerry was just saying, you could be measuring an asteroid or you could measure a star.
Yeah, it doesn't matter what object. But he may be referring to the distance from the filter to the CCD. Is that what you're talking about?
I think it was distance to the object.
Oh, yeah. Okay, all right. No, the object doesn't matter. It's just the light. Yeah. Light from any object.
Mm-hmm.
Mm-hmm.
All right, we'll talk about.
So I guess one thing we can talk about is the exoplanet measurement. Now we did our first exoplanet measurement using this filter and this new scope, and it's I don't know if you've got the link to that. I guess you can share that. But we basically submitted that data that Bart Ballard and I did this observation about 2 weeks ago, I think it was.
Okay. And
submitted it to the Czech. There's a database called the Exoplanet Transit Database. It's in Czech Republic. It's managed by that university over there, and so it was our first one, and we were able to do that successfully. Even though it's a little tedious. You have to do a fine calibration. You have to manage your exposure so you don't overexpose the star. You have to manage that and make sure it's bright enough to be able to do small and the noises level is small when you do the calibration. The background noise is what I'm talking about. So you want a high signal to noise ratio on the measurement, basically. And then you couple that with a lot of readings, so you're able to average out the pre-transit, where you have, the stars fairly steady, and then you have the post-transit level, and then you have the slope of when the ingress and the egress, just like when Venus transits, you have an ingress and an egress, and then you have the depth of the transit, and in this case, it was around 10 millimag, or basically 0.01 magnitude, or 1% magnitude. So that was the depth of this transit, and we even though you've got a lot of scatter in the data, once you average it out, you can detect the transit and fit a curve to it, and that's what you'll see on that website, is the curve that our data was fit to, and then from that curve they calculate these different parameters for the exoplanet, how big the planet is, where it's located, as far as the inclination angle, whether it's down towards the bottom of the star, whether it crosses the middle of the star or near the top of the star. And you can see in our case, this was HAT P1, I think, WASP 51 Bravo. Is that right? I think that was the star.
Yeah, WASP -51b.
Yeah, so that one, right? So that's the one we measured, and it's pretty, pretty small depth to be tackling with the 6.5-inch telescope. Most people use, most of the people that do this work are using 24-inch telescopes, or even 16-inch telescopes. But we were able to do it with a 6.5-inch telescope.
Nice.
What constellation was this star in? Didn't even look that up.
I'm trying to remember. I don't remember.
Let's see if we get some coordinates here.
So, Jerry, if somebody were just starting out with imaging or with the exoplanet hunting, what would you recommend? Say somebody like me who mostly uses a, say, 8-inch, 10-inch manual reflector. So
if you're starting out, one thing to understand is these measurements are very precise.
Yes.
So
it's a little intimidating, actually.
They are. It's a little bit of work to learn, for sure. Typically, you can't just jump right into it. You have to understand all about CCD image processing in a scientific way, not on a pretty picture way, but in a scientific way where you run calibration frames. And so what calibration does to the frame is it minimizes the amount of noise. You're trying to maximize the signal of the star, the brightness of the star, and you're trying to measure it precisely, which means you minimize the amount of noise.
So you definitely want to do astrophotography 101 before jumping into I want to find a planet.
Right, exactly. So that's not to say that. Now, one of the things you can do if you're really interested in starting out with trying to measure and do light curves, which is what we're talking about. We're talking about light curve work, which is a general method of measuring any stellar object and measuring the changes in the brightness of the object. So you've got several different objects you can use. You can do asteroid light curve work, which you can calculate the rotation period on. You can do exoplanet work, which is a much more precise measurement. You can do eclipsing binaries, which is a very easy way to get started in light curve work because the magnitude change is much higher. You can get magnitude changes of 0.5 to 1 to even greater than 1 magnitude.
And if it's something like Algol, it's very predictable and very well known.
Exactly. That would be a great object to start with if you want to get into light curve work and figure out how to do imaging and how to plot the data, how to gather the data, how to measure the brightness of the star, and then how to plot the curve. And then you can tell a lot from that. You can get the times, the transit time and all that other stuff, and compare it to what's published and say, oh, yeah, I was able to repeat the measurement that these people are doing. So that's a great start.
The one that you just did, was that, would you put it on the level of difficulty? Was this like the first one you've ever done? So,
Yeah, we started out, well, the way we started, Bart and I took the AAVSO class. There's a program on the AAVSO called Choice, and it's a bunch of classes you can take on different things. One is like the one I was first involved with was creating a variable star observing program. And the course that Bart and I took, which is they offered, and I think it's offered this February, is last February Bart and I took it, and it was called Exoplanet Observing. And it's taught by a great guy. His name's Dennis Conti, and he's the AAVSO group section coordinator for exoplanets. And he does a great job teaching the course. And so Bart and I took this last February, knowing that we wanted to start observing exoplanets with the MSRO. But we didn't get to it until like 2 months ago. So we started planning our first observation about 2 months ago, and we got in the weather and timing of the exoplanet. All this stuff goes into how you plan for the observation and make sure it's in the right spot in the sky. Our sky is not the best in the MSRO as far as horizon goes, but we were able to get all those things come together, and then we go to measure it. Okay, then we do first observations, and one of the things we ran into was, of course, clouds. So all the things come together for that transit. All the stuff comes together right, except for the weather, of course. So it took us about a month and a half to get to the point. We had done 2 attempts on other exoplanets that were available to observe, and we did one where we did a partial where we just saw the ingress. We didn't catch the egress.
Yeah.
And then so this was the first one we were able to do both sides of the transit. And actually, I think we actually had to do a peer flip in the middle of this transit measurement also, but to correct that.
And all about that.
Yeah, so if you have a German equatorial mount, you have to contend with the peer flip, and that's why most people that tell you that if you want to observe exoplanets, they suggest you use a Schmidt-Cassegrain on a fork mount that doesn't do peer flips. But it's doable. And it's not a thing that you can't overcome. It's just one more thing you have to accommodate for. That's all.
Mm-hmm.
So Bart and I did that.
Well, to let everybody know in the listening out there, what that means is if you have a standard German equatorial mount and a refractor, a lot of people have, even a small one, does the same thing. If you want to look at something in the western part of the sky or something on the eastern part of the sky, well, let's say you start out looking towards the eastern part of the sky and your scope is moving along with the Earth. There's a point where your eyepiece end will actually hit the mount or your tripod. It won't go any farther. So you have to take your scope, move it around the tripod or around the leg, and basically you kind of flip your scope, twist it around so that it's now on the opposite side of the pier so that you can look towards the west side of the pier. Well, that means you have to actually stop in the middle of your observation, especially if you're driving and tracking and photographing something. So you have to stop, twist it around, reset it so it's going to move away from the leg on the other side of their mount. And yeah, it's just disruptive to do that. Especially when you have something like an automatic, scope that tells you that it's going to hit and it just stops your scope and doesn't flip it automatically, and you don't get a notice. That can be kind of bad. You have your scope why did your scope stop all of a sudden? Well, it's because it was going to hit something.
Right, exactly. And that's basically how we have our system set up at the MSRO. We have it stop on the meridian so that we can manually manage that. Of course, our system's not set up as an fully automated system. It's a hands-on system, so that's why we do it that way.
Mm-hmm. And well, if you're around your scope too, we had to learn lessons like get ready to move the ladder.
Oh yeah.
If it does an automatic flip and you've got a ladder there and you've walked out of the observatory and let it run on its own, it might actually flip into the ladder.
Oh yeah.
Not a good thing.
So before we hit the bottom of the hour, Jerry, we've got another question from Glenn. He wants to know, have you seen something no one else has?
I would say no. it's hard to discover stuff. It's very difficult in today's environment with everything having been discovered on that you can see with even a fairly large scope, like a 16-inch scope. Even most things that you can observe with a 16-inch scope has already been discovered, basically, except for comets. Now, if you're lucky enough to win a lottery, then you can discover a comet. Anybody can discover it. And also, if you're lucky and you're looking for, like, say you're pointing you're imaging some out of the ecliptic, basically, or north or south of the ecliptic way, and you just happen to discover an asteroid that's a random thing.
Mm-hmm.
You could discover an asteroid for sure that's brighter than normal, than what that could be like 15th magnitude maybe, or even 13th magnitude, just randomly come across the north sky, the North Pole or the South Pole. Theoretically you could discover that, because people aren't searching there for asteroids per se.
Yep.
So, but it's difficult.
Now this star and planet that you observed, it hasn't been observed for a while, you said.
Yeah, this one, if you look at the database on that website, it hadn't been observed for almost 2 years. So that's pretty cool, being the first person in 2 years to observe this transit. Mm-hmm. And it's interesting to see, and it's cool because over a 2-year period, you don't know what kind of changes could have happened to the orbit of that planet,
Mm-hmm.
You have an idea if something could have changed. Maybe the original observations were off for some way, and then when you look at it again, some of the data's different, that type of thing. So in that regard, you can discover changes in objects that have already been discovered. So that's really what we're looking for as amateurs, is keeping up to date with what's going on with these objects. And they're called follow-up observations. Of course, the professionals do discovery, and amateurs do follow-up work to keep track of stuff, to see how things are going.
Let's do a little station identification. You are.
Arr.
All right. Listening to Space Pirate Radio here on Astronomy.FM. It is, of course, another Wednesday evening, and this one is January the 24th, 2018, 9:32 for those of us here in the eastern portion of North America. Universal time, that would put it at 2:32 Thursday morning, January the 25th, 2018. So we still have half our program to go. We've been live for the last half hour. Of course, that means we have our Astronomy.FM chat room wide open for you to come on over and join us. Get to the homepage at Astronomy.FM, and you'll see near the top where it says Radio Chat. Just click on that. Type in a name, hit the word login, and you'll be here in our chat room. If you want to ask Jerry a question, please, or me or Dianne, please feel free to do so. We're trying to read our chat room as we go along here. And we'll put some links if we have something to show you. We'll put links right in our chat room, too, which you can also get those links on our Space Pirate Radio Facebook page, too, if you want to get back to those. Really good for people that are listening in during the repeat time to catch those links on the Facebook page. And then you could look at the things that we're talking about during the repeats section. So far, we've got the chat room. We've got you and me and, me, Dianne, Jerry, a couple of, we got an on here, number 332603. Yeah, you can log in as anonymous too. Twist Edge, Glenn, Doug from Northern Cross Observatory, Plaid Mac, Plaid Sister, Optronics, and Plaid Joan. Glad to have the Plaid Sisters in here too. Didn't catch you at the beginning, so all of Plaid Max.
Clan,
yes.
Clan.
The Plaid Clan. We're all part of the crew here on Space Pirate Radio when you come into our chat room, so glad to have you all here. All right, let's keep on going. We've been talking with Jerry Hubble, talking about the Mark Slade Remote Observatory upgrades. And doing some,
and how we've been using the recent equipment that we've installed
for exoplanet transit. So it can be done by an astronomy club.
Yes, yep, it can be done. It just takes a little bit of, more than a little bit of skills and training. Mm-hmm. But you can do it. Anybody can do it if they take the time to learn.
Now, do you have a wish list for the observatory of a scope that you would ultimately really like to end up with, or you think you're there?
No, well, as far as Explore Scientific's been a great sponsor for the observatory, and I'm glad that we can do that. One of the things that Myron Wasuda, who was on the last program with me, would like to see is of course a larger scope, a larger light grasp, like a 12, or I'd like to see a 14-inch, but an RC scope like a truss tube, Ritchie-Chrétien scope,
Nice.
And there's they're getting pretty inexpensive considering what they used to cost. Astrotech makes a great one. I've got an 8-inch version, a carbon fiber 8-inch tube version, but they make a 14-inch and a 16-inch truss tube for I think it's around $5,000 to $6,000. I mean, that's a lot of money for most people for sure. But when you talk about an observatory, a permanent observatory, it really is inexpensive to get that large of a quality scope. I'm sure if people go out there and look at the Explore Scientific webpage and look at the scopes that we've got installed in the observatory, they'll look at the price and say, "Oh my gosh!" For a 6.5-inch scope, that's what I'm paying. It's like, but refractors are in a whole different.
Absolutely.
They're different than reflectors. You're never gonna get the light gathering capability of a reflector at an equivalent cost for a refractor. So there's just no way around it. So what you concentrate is on quality and light not light gathering per se, but you want the quality of the image, and that's paramount. And I think for the most part, refractors always can outperform for image quality. If you take like the 6.5-inch is, I consider it equivalent to like an 8-inch size reflector scope because of the obstruction and everything else that goes on. So that's kind of the way I think about it. And for an 8-inch reflector, now Newtonians come close to sharpness, but you got to have corrective optics in there also, just like you have to do. And even with this 6.5-inch refractor, we have a little bit of corrective optics in there called a field flattener focal reducer. So nothing's perfect right off the bat. You always have to massage it, but you can get near perfect flat fields and a wide field of view on these refractors. It's pretty amazing where we're at with today's technology.
Well, definitely mention the Ritchie-Chrétien, how that's different.
That's a reflector with now most Schmidt Cassegrains have a spherical main mirror. RC scope has got it's a hyperboloid shape. It's not a spherical. It's not easy to grind. Let me put it that way. The secondary is the same way. So the thing about and one thing with a spherical secondary and primary on a Schmidt Cassegrain, it's easy to collimate it. Okay, where on a hyperboloid shape, you've got to worry about. You can't just rotate it. You have to move it, shift it to get it to collimate. I may not be 100% correct on the movements, but it's much tougher to collimate because it's not independent of angle. There's a lot of little factors that go into collimating it. So in that regard, it's a little tougher. It's a very good instrument though. It's better than a Schmidt Cassegrain as far as image quality goes. There is some field curvature, but you don't have the coma. I don't know if you remember, even the newer Schmidt Cassegrains are better, but the old Schmidt Cassegrains, you remember the coma that was on the edge of the field, even a small field of view where the stars turn into little cones, shaped objects. They're not spheres, they're not circles, and that's the kind of problems you have with spherical objectives. So that's the main difference. It's just the quality of the image. And the Hubble Space Telescope is an RC scope, and most professional scopes are RC scopes.
And they're mostly made for a camera, if I'm not mistaken, too.
And you don't really call them telescopes; they're called astrographs, which is a fancy term for telescope that just makes images and you don't typically look through them with your eyeball.
It generally has one focus sweet spot, and that's it.
Right.
So you put your camera there, and if you had an eyepiece there and you change eyepieces, you move it in and out. Well, that doesn't work with an RC. You have one good focus spot. The two mirrors have to be the perfect distance from each other, and then you get one spot focused at, and that's where you put your camera. And
right, exactly. Right. Uh-huh.
Now and what we're talking about, field of curvature. Let's say you put a flat piece of film, the old style film. You put a flat piece of film on there. Well, you find out that right in the center, everything's focused, but off to the edges, it's not quite focused. And the way to correct that would be if you could physically curve, kind of make your film a little bit bowl shaped, then it would be focused more out to the edges. Of course, you'll get glass plates, the old style glass plates. You couldn't bend those things.
No, but I know they used to try to do that with a vacuum chamber on the backside of the plate. I think I've read about some of that.
Yeah, I think I remember too. You don't get much bending, but a little bit to basically get your focus spot a little farther out.
Right.
I don't think they make curved CCD chips either, do they?
No. But that'd be interesting. I don't know why they couldn't.
Yeah,
Think about
a concept.
That is a cool concept when you think about it. Especially at the bigger chips, you need it.
Yeah.
But how we do it with corrective optics is what we do now. We got field flatteners, is what they're called, to correct.
It's actually basically straightening out the light instead of trying to bend the chip or the film.
Exactly.
Yeah, I remember some old, even for celluloid film, there was a frame holder that you could put it in. It would actually kind of bend the old style film. Not the glass plates, but the plastics.
Right.
Let's see. Explore Scientific. What's new there?
Explore Scientific. So one of the things we use the observatory for, to segue out of the observatory, is to test the equipment. And I don't know how many people that are listening know, but I designed our control system that we sell at Explore Scientific. It's called the PMC-8. It's a mount controller that I basically designed from scratch about 4 years ago. I started on this project, and we've been selling it for almost a year now, and it's been very successful. I'm really pleased with the way it's turned out. It's been a lot of work, but I basically designed the whole system, the hardware, the electronics. I designed the circuitry. I did the firmware for it and did a lot of the software that's available for it now. We offer a standard, and it's different in some respects to most other ones that are offered out there. We're wireless right off the bat. You don't have to have an add-on piece to add wireless to your controller. It doesn't have a typical or standard hand controller system with physical buttons, and it uses a tablet system. And we're getting ready to release our Android app for it. We've got a Windows app for Windows tablet right now called Explore Stars. We're getting ready to release the Android version of the Explore Stars application. Nice. And I wrote the ASCOM driver to be able to use it with all the standard PC software that's out there that most people use to do astrophotography and run their observatory.
Tell everybody what ASCOM is.
Yeah, ASCOM is a standard. It's a standard for interfacing to astronomy equipment. It's on the Windows platform, and it allows you to create client software or like programs, like a star chart program or a camera control program that talks to the ASCOM driver. It's a standard interface, so that the application developer doesn't have to go back to the manufacturer and say, I need your driver, I need to code to your driver, and then it goes to another camera manufacturer, I need to code to your driver. So the application developer doesn't have to write all this different code to talk to each individual camera or each individual mount. Each mount's going to have a slightly different control language. Each camera's going to have a different control language. So the ASCOM driver shields all that, okay? It's a standard API. It's like COM, like for printers, okay?
Mm-hmm.
You don't want to have you don't have to write a program that talks to a printer. You don't want to have to code for every stinking printer that's in the world, thousands of printers. So under Windows, you have the Common Object Model, which is a COM. That's what COM means, a Common Object Model. So everybody creates a COM driver for their printer so that any program that uses a printer can just talk the same language to the printer. And then the COM driver translates that into the specific commands for that printer. And that's the same way it is with astronomy equipment. That's why it's called ASCOM, because it's astronomy COM.
It's a international. It's a what do they call them on Star Trek? The that allows people to talk to any language.
Translator, yeah, universal translator.
Universal translator.
Right. Yeah. Exactly.
There you go.
So I wrote the ASCOM driver for the PMC-8 so that any client program like MaximDL or Carte de Seal or Stellarium or any other, of the programs that are out there that want to talk to the mount, just connect to the ASCOM driver and start using the mount. They don't have to know our command language. Mm-hmm. Now, one of the other features of our system, which is kind of unique, is that we offer it's an open source. Our software is open source in the fact that we share our source code on how to actually talk to our controller. So you can use it as you see fit to write your own programs directly to the controller. You don't necessarily have to use the ASCOM driver if you don't want to. Like if you're developing a program on Linux or on Apple, iOS, if you want to create a program on iOS that talks to our controller, we give you the example code and some of the actual command language and other things. We got a whole software development kit to be able to write programs on iOS that allow you to talk directly to our controller and use it the way you see fit.
So you can, is your system made for pretty much any scope that would be?
Any mount, you mean?
Yeah, any mounts.
Theoretically, yeah. I could retrofit this controller to any mount basically that we could drive with a stepper motor. Mm-hmm. It's just a mechanical thing more than anything. So, and in fact, we sell the mount right now on the Losmandy G11. So we created an adapter to adapt our motors to that system. And we also offer it in the Exos 2 mount that we sell, which is a lower end mount, or that we sell the PMC-8. And we're getting ready to release products in that line this year. So we can talk about that later on this year once we release that stuff. Mm-hmm. But we also offer a retrofit kit on the G11 now, where you can, if you've got an old G11 that's 15, you upgrade the control system on it, you can you can have our system installed on your mount. So that's just, and I think more of that's going to be coming. So there's no reason you couldn't adapt our controller to just about any mount.
And what can you use to run your controller with?
As far as
planetarium programs, things from your computer?
Yeah. Yep, any kind of planetarium, like we use observatory control program called MaximDL. Mm-hmm. We control the mount along with all of the other instruments. But there's any number of programs that are standard clients that talk to mounts that you can connect to it too.
Could you do it with Stellarium?
Yeah, Stellarium works. Mm-hmm.
Okay, cool. I always promote Stellarium because it's free for everybody. So.
Yeah, and I like Carte de Seal. That's another free program. And then there's other ones also. I know I've got a program that I haven't used recently, but I think it's called Astroplanner. I don't know if you've heard of that one. It's a nice planning software connect. Also, but a number of them out there. And we list them on the website. If you go to our website and look under PMC-8, you'll see we list some of the things that you can use with our mount.
Okay. Now, obviously, you can control the mount to point to anywhere. What about things like tracking for astrophotography?
Yeah, and that's really that's one of the things that I tried to do with the design of our PMC-8 was to make it as, and the acronym means precision motion controller. So it really gives you fine control over the mount, and especially tracking. So that's one of the design goals of the system, to set the tracking rate as to very fine value. And what that allows you to do is to, and we implement this in our Explore Stars application, is to be able to plop your mount down, okay? Let's say you don't do a very good polar alignment. It's within 5 or 10 degrees, okay? You'll use our Explore Stars app to do a 2 or 3 star alignment.
North from here is over that telephone pole from my backyard type of thing.
Right, exactly. And then so when you're not on the pole physically, as far as your mount is aligned not with the pole, it won't track accurately because you're off a little bit. You've got some declination drift and you got a little bit of RA tracking error. So what our mount controller allows us to do with the Explore Stars app is, once you've got the alignment, it's basically an internal model of the sky as compared to your mount, where the mount's pointing compared to the sky, and it'll adjust the rate. The behavior is such that the rates on the RA and the declination axis are dynamic. And it's kind of like what happens when you have just an Altaz mount and you're tracking the sky with the Altaz mount. You have to change both axes continuously. So that's basically what this controller does, allows it to adjust the rates continuously. Although that's not how it's doing it, but that's what the effect is, to where it's keeping the object centered in the eyepiece, basically, or on the frame.
We have questions that do auto guiding.
Yes, auto guiding.
All right.
And in fact, the implementation of the first release we had last year, we used the standard ST4 guide port off, with a camera connection. But I'm getting ready to release an update that will use pulse guiding through the ASCOM driver. If anybody's aware, knows what I'm talking about there.
Doug does.
Yeah, so pulse guiding is really where everybody wants to go. But we didn't implement that right off the bat initially, because we had some deadlines on what we were trying to do, and we had to get it all working and released last year. So we went with the auto guider port. We figured we'd support that, and most people can use an auto guider port physically. It's a little easier. Most cameras, or pretty much all the cameras that are out there, support the ST4 auto guiding port, so that's why we implemented that first. But I'm getting ready to release a new ASCOM drivers version that's going to have pulse guiding in it. And all that means is that it's sending the commands over the computer connection instead of going through the camera physically through a contact closure type of connection. So that's the old style. The ST4 port was like an old hand controller where you had push buttons. It basically mimics that. Where you just, and in fact, you could plug in the PMC-8, you could plug in a simple push button hand controller into the guiding port and use that for guiding if you wanted to.
Interesting.
The old days.
Yeah. I am the old days. Oh, well, let's talk just some general astronomy stuff. So I wanted to get in before the end of the show. Lunar eclipse coming up.
Yes.
Next Wednesday, but I looked it up for sure. Wednesday morning. So basically, kind of like staying up all night long Tuesday night, or getting up very early Wednesday morning. Mostly visible from the Pacific Ocean. So if you're somewhere near somewhere in the Pacific Ocean, you're doing pretty good. Well, most of it anyway. Central, Hawaii's going to be real good. So the farther off you get from that line, the less you get of the eclipse. I've seen eclipses like this, as when the sun's rising out of the east, the moon is setting in the west, and that's when the eclipse basically kind of starts for us here in Michigan. So we might get a piece of it if we've got an incredibly clear western horizon and a really, really low horizon, like being along the Great Lakes or something like that.
Yeah, I think I recall waiting up for one of those once, and it wasn't worth it.
I have seen
from where we are.
Yeah, I've done some of those before. So those of you, Western Canada, Alaska, Australia,
to be
China, Russia, Japan.
Yeah. So
pretty good.
From the continent of North America, for the entire eclipse to be visible, we're talking British Columbia and up. So we've got Sky Intel has a pretty helpful map that shows the bands. And so it looks like it's going right through Vancouver Island. So where we are, Michigan itself, the moon sets during total eclipse, except in maybe the extreme southeastern corner of Michigan where the moon sets while it's still entering the umbra.
So partial total.
Yeah, so anybody to the east of us, no, sorry.
Yep.
Or unless you're going due north through Ontario. This is pretty more advantageous if you're Canadian than if you're in the lower 48.
Yeah, the farther north you are, the better, and the farther west you are.
Yeah.
For the best views of this. So most likely I will be missing this one. I don't have a good...
You can hype it up as the super blood moon, blue blood super moon, blah, blah. No. It's a lunar eclipse.
Royal moon. I call it a royal moon. I don't care. I want the pizzazz to it. So that's all there is to it.
People like to name all kinds of stuff nowadays. It seems like, every storm, every winter storm now has got a name.
I know.
It's like they're getting carried away with these names. I guess it's easier for people to remember.
Let's see, got some in a couple days. The moon's going to occult some stars in Taurus on January the 27th. Let me just put this link in here for everybody. And again, it'll be in our Space Pirate Facebook page too. So check it out. So yeah, 27th there's going to be like 4 stars of 4th magnitude and brighter that are going to be occulted by the moon. That means the moon's going to go in front of those stars. So something to check out if you're in, let's see, Canada, Alaska, Northeast Asia, Canada, Alaska, Greenland, Easter Island. Oh boy, Easter Island's going to see this. And North Alaska, North Canada, North Greenland, give you an idea where that action's going to happen. And then I don't think we're back by then. February the 1st, if you're in Northern Europe and Northern Asia, star Regulus will be occulted by the moon.
Ah, that's a nice one. Nice bright star.
Yep.
Occulted by the moon fairly often.
0.4 magnitude. Do you do any lunar occultation?
Yeah, actually, I remember the fellow that I work with for the exoplanets, Bart Ballard. He's heavy into occultations, and he's done quite a few over the last couple of years. Yeah. So,
I forgot to mention you have somebody using your scope remotely.
Oh yeah, we're doing training. We've got one fellow in particular. He's from Bangladesh. He's a PhD student that's working with Myron to learn our system. He's doing some observations for a project he's doing on variable stars, and he's been working with Myron on that for the last, I would say, couple months, probably getting trained up.
How long does it take to get trained up, you think?
Well, I would say probably 20 to 30 hours of work.
Okay.
And then I kind of grill people. I do the final exam to make sure they understand the system, so that the main thing is to understand the system so that when you have a problem, you'll be able to solve it yourself instead of having to call Myron or myself to solve it.
It's always good to know what's going to glitch.
Jerry, courtesy of the chat room, we've got one last question for you. And we got 90 seconds to answer it.
Okay.
What is your biggest wish? I assume astronomically speaking.
My biggest wish? Well, I'd really like to build a much larger observatory, and like at least a 24-inch or maybe even a 30-inch telescope in it with some high-end. I guess my biggest wish is to be able to spend $100,000 or more on an observatory and have use of it. You can always rent time on telescopes, but there's nothing like owning your own. Yeah. I can say that.
One quick note for optronics: there's a nova in the constellation of Musca. It's very, very southern hemisphere. It's actually like 25 degrees from the southern pole. So 7th magnitude, not too bad. Anybody lives down that way, get a chance at it. Well, it's time for us to head out of here. So, Jerry, I really want to thank you for joining us tonight. Appreciate you being here.
Sure, yes. I very much enjoyed it. Thank you.
We'll certainly get you
Always
back
a pleasure.
again. And thank everybody that's been in our chat room tonight. Appreciate it. Don't forget, we got more programming come up. Astronomy Ireland, Planetary Radio, Planetary Scientists, Naked Astronomy, Naked Scientists, all coming up next. Thanks all. Night.
Clear skies, y'all.
We hope that you've enjoyed this program from AFM Radio, the broadcast service of Astronomy.FM. This program has been released under Creative Commons license. Please contact us for details. You may find more of our AFM original programs on our website. It's really easy to find us. We are Astronomy.FM. You may also find us in the iTunes radio listings near the top of the News Talk section, and also as an iTunes podcast selection. We'd love to hear your comments. Please email us at radio@astronomy.fm. Thanks so much for being part of the voice of astronomy around the world and across the known universe. This is Astronomy.FM Radio.
AFM.